All right, so while waiting for the others, so this is now your chance to ask a question. So anyone who has a clarification? All right, so may we continue now our discussion?
Yes, sir.
All right then, so this is where we've stopped by solving the I sub 2. For the I sub 1, okay, you can actually substitute this one already, the value of your I sub 2 on the equation 1 or 2, okay? But just to show you guys, or just to show the simultaneous equation, okay, so we can also do that one by eliminating the uh, I sub 2, okay, by retaining the I sub 1. So from here, let me just erase this one. All right. All right. So from here, okay, for us to be able to eliminate the I sub 2, so we have to multiply a certain number on both equations. So times 3 right here, and then times 2 on the second equation. Okay, so negative 20 times 2, 56, 84. So yeah, it's 84. So we'll be having a negative 84 right here. And then, so 6 times 3 is 18, plus 18 I sub 1. And then 2 times 3 is 6. So plus 6 I sub 2 is equal to 0. And then on the second equation, so we'll have here negative 14 plus 4 I sub 1. And then plus 6 I sub 2. Okay, so there you go. So we now have the same value for the equation 1 and 2. And then just perform subtraction. Okay, so 6 I sub 2 minus 6 I sub 2 is, of course, 0. Okay, and in here, 18 I sub 1 minus 4 I sub 1 is equal to positive 14 I sub 1. And then right here, so negative 84 plus 14, you'll get negative 70. So from here, you can now simplify this one a little more, wherein it will give you I sub 1 is equal to positive 72 divided by 14. So I sub 1 is equal to 72 divided by 14.
So it should be 70.
Hmm?
70, not 72.
Ah,
70%.
sorry. Okay. So this one was supposed to be 70. 70, 70. So 70 minus 14 is equal to a minus, divided, not minus, is equal to 5. So there you go. You now have the current for the I sub 1. Okay. So I sub 2 is negative 1 amps, and then I sub 1 is 5 amps. Okay. So we're drawing the circuit. So we have here a 5 amperes with this direction. And then we have here negative 1 amperes, meaning it's just that the assumed flow of current in here is not true. Okay, it's the other way around. So this one should be flowing the clockwise, okay, the conventional method. All right. And what else? The solution of negative 1 amp for I of 2 means initially assumed direction of current was incorrect. Okay, so the direction of the current was incorrect. So just change this one into clockwise. All right. And what else? Change of current direction. All right. So more explanations. So I will not read this one anymore. So I'll leave the reading part to you guys. And then right here, so I1 is going down through R2, while mesh current I sub 2 is going up. So they now have two different flow of current. Okay. So for you to be able to determine the actual current through R2, okay, so is it really the I1? Is it really the I2? Okay, so you must see how mesh currents I sub 1 and I sub 2 interact. Okay, or let's just say that which one has a higher flow of current. Okay, so of course, by nature, whichever has a higher amount of current that is flowing is the one who's going to win. Okay, so that is why, as you can see right here, we have performed I sub 1 minus I sub 2. That is because I sub 1 is higher, then you have to deduct the current that is opposing that current. Okay, so I sub 1 minus I sub 2 is equal to 4A, or 5 minus 1 amp is equal to 4 amps. Okay, and then your 1 amp here, right here, is just flowing on the R sub 3. Okay, so in that case, we don't have a contradicting currents that is flowing down below and then going upside on the other side. Okay, and basically it's a common sense already, since we have a higher voltage source on the left side compared to the right side, okay, which is just 7 volts. Okay, so the higher of flow of current wins. Okay, so this is the best explanation with this one. All right, so at this point we have 5 amps, and then it will be separated by 2. So again, by applying the KCL, so entering the node must be equal leaving the node. Okay, so 5 amps is equal to 1 amp plus 4 amps. Okay, so are we clear so far up to this point? Hello? Any question or clarification so far?
None, sir.
None, sir.
Wala pa naman, sir.
All right. Okay, so let me just mention the advantages of mesh current analysis. Okay, so the primary advantage of mesh current analysis is that it generally allows for the solution of a large network with fewer unknown values and fewer simultaneous equations. So our example problem took 3 equations to solve the branch current method, okay, and only 2 equations using the mesh current method. So if you're going to perform the not I mean the Kirchhoff's law, okay, the old way, so you will have here a 3 equation. Okay, so 2 kVL, okay, or even 3 kVL, so that depends on you, and then 1 kCl, so giving you a total of 4 equations. But in applying mesh, okay, you will only get 2 equations, just like what we have a while ago. So 1 equation for the loop 1 and then another equation for the loop 2. So in that case, it is a lot easier to solve a simultaneous simultaneous equation okay, rather than having 3 or 4 equations. Okay, so this one is much bigger than this. Yeah, okay, so this one is very true, especially if we have a greater network increase in complexity. So the more complex the circuit, the more advisable to use the mesh current analysis. So if it's just up to 3 equations or 4 equations, yeah, you can still use the Kirchhoff's law. However, if it's 4 or 5 or 6 equations already, then it's not advisable to use the Kirchhoff's law already. Okay, well, you can still use it one. You will still be able to get the correct answer. However, it will take you longer than, or if you're not, or if you will apply, okay, the mesh current analysis. Okay, so what else? Solve the central function. All right, so just like what I'm saying a while ago, so if you're going to use the old way, so you will get 5 equations in here, and then so two KCL equations, and then 3 KVL for this one. However, if you're going to, where is that one? The form of the KCL equations. Okay, so I guess it's on the next part. So it wasn't able to mention in here, but if you're going to use the mesh current analysis, you will only have 3 equations in here. Okay, so equation number 1 for the loop 1, and then equation number 2 for the loop 2, then equation number 3 for the loop 3. Okay, for the Kirchhoff's law, you'll have 2 KCL equation and then 3 KVL equation. Okay, so 1 KCL on the node 1 and then 1 KCL on the node 2, and then 3 KVL on each of those loops. Okay, so here's the example analysis using the Kirchhoff's law. So we have 2 KCL and then 3 KVL. Okay, so I'll leave the analysis part to you guys, okay, since it's already in here. So we have here for the node 1, node 2, loop for the left, and then loop for the middle one, and then loop for the third one. Okay. However, if you are going to use the mesh current analysis, you will only arrive with 3 equations. Okay. So those are just some explanations. So I'll read everything anymore since we are now lacking in time. Okay. So it says your last equations to work with a decided is a decided advantage, especially when performing a simultaneous equation solution by hand without a calculator. Okay. And yeah, so were you guys able to follow up to this point? So those are just equations anyway, or the process behind mesh analysis. Okay. So can you guys still follow? Are we still clear?
Yes, sir.
Yes, sir.
Okay, so my only point on the last few slides is if you're going to use KVL, you'll have more equations, like 5 equations. But if you're going to use mesh analysis, you'll have 3 equations only, right? Okay, so let's have this another example. So unbalanced Wheatstone bridge. Okay, this is very famous, especially that this one is not solvable by Ohm's law. Well, there are others who were able to answer this one by Ohm's law, but mostly we use mesh analysis with this one. Okay? So this is another type of circuit that lends itself well to mesh current, is the unbalanced Wheatstone bridge. So take the circuit for example. So since the ratios of R1 and it's parallel with R4, okay, and then R2 is parallel with R5 are unequal, okay, so we know that there will be the voltage across resistor R3, okay, and some amount of current through it. So this type of circuit is reducible by normal series parallel analysis. So you cannot just simply combine R1 to R4 and then R2 to R5 and then have a series connection. Okay, so you cannot just do that one. Okay, so this one can be only analyzed by some other method. So what are those methods? Like for example, the one that we are having right now, the mesh analysis or the branch current method. Okay, but it would require 6 currents, so I1 through I6, leading to a very large set of simultaneous equations to solve. So using the mesh current method, though, we may solve for all currents and voltages with much fewer variables. So yes, this is also solvable if you're going to use the Kirchhoff's law. However, it says here that it will give you 6 equations. But if we're going to use the mesh current method, so it will give us a fewer equations. Okay, so of course we're going to use the mesh analysis. Okay, so we're going to have the first 2 loops in here. So this is your first loop, and then this is your second loop. Okay, but if you're going to take a look on this one, uh, we're going to apply KVL, but in I1 and I2, we don't have voltage. Okay, so that is why we have to apply another loop in here, which will be your loop number 3. Okay, so we have here your I1, I2, and then I3. So the direction of this mesh current, of course, is arbitrary. So we just assume it again. So this is not the correct, or we're not yet sure if this is the correct flow of current. However, 2 mesh currents are not enough in this circuit because neither I1 or I2 goes through the battery. So we must add a third mesh, which is the current I sub 3. So just like what I've explained a while ago. So here I have chosen I3 to loop from the bottom side of the battery through R4, through R1, and back to the top side of the battery. This is not the only path I could have chosen for I3, but it seems the simplest. Okay, so you can have the other way around. Okay, but in the opinion of the author, okay, so this is not my idea. Okay, so this is the idea of the all about circuits. Okay, this one came from a website, so this is his own dialogue. Okay, so now we must label the resistor voltage drop polarities. Okay, so once you're done in having the loops, then you can now label everything. Okay, so let's just say that you're done with your labels. So we have your positive, negative, positive, negative, negative, positive, negative, positive. So notice that something very important here at resistor R4, okay, the polarities for the respective mesh current do not agree. Okay, so this is one thing that we should always avoid. But there are some cases that we cannot really avoid it. Like for example, this one. Because if you're going to do the other way around, okay, and it will just lead you to have a contradicting symbols with your R1. Okay, so in this kind of scenario, it's inevitable. Okay, so we cannot avoid it anymore. So this is because those mesh currents I2 and I3 are going through R4 in different directions. Okay, I2 and I3. I2 and I3. Yeah. So we have here negative positive and then positive negative. So this does not preclude the use of the mesh current method of analysis, but it does complicate it a bit. Okay. So yeah, just like what I mentioned a while ago, you can still have a opposing symbols, but it is a little bit more complicated. Okay. Though later we will show how to avoid R4 current clash. Okay. So it's the example below. Like right here. Okay, so this is the generated KVL equation from this bridge. So we have here, so where did it start? I sub 1. Okay, right here. So positive 50 I sub 1. So he chose to have the first symbol and then followed by the next one, which is positive 150, yeah, which is positive 150, I1 plus I3. So you're going to use plus here since they have the same symbol. And then for the last one, we have here plus 100. So right here, plus 100, I1, and then I2. So since they have the same symbol, it's plus again. All right. So were you guys able to follow the equation number 1 for the loop number 1? And how did we get this one? Or would you guys like to have our own solution? So I'll just explain it right here for us to have a step-by-step solution. So at node, at loop number 1. So KVL at loop number 1. Okay. So in here, you chose to get the sign on the first, okay, wherein it will enter the component. So we have here positive 50 R sub 2, okay, and then positive 150 I sub 1. 150 I sub, this is R sub 2. Sorry for that one. This one is I sub 1, okay, and then the next one is plus 150, okay, so this one right here, plus 150 times I sub 1. Okay, but then again, there is another current that is flowing on the other side. So you should also consider that one just by looking at the sign. Okay, so we have positive, positive, and then negative, negative. So in that case, they will add up with each other. Okay, so I1 plus I sub 2. For the last one, we have positive 100 times I1, and then again we have another current that is affecting, okay, this R sub 3, so we also have to consider it one. So if you're going to take a look at their sign, so we have positive positive and then negative negative, so they will be add up with each other. So I1 plus I2, right, equal to 0. So this is our equation number 1. So were you guys able to follow?
Sir, bakit plus? Ay, pa-clarify lang, sir.
Why plus? Because they are flowing with the same direction. Okay, so your only sign, okay, that will differ is, like, for example, right here, we have positive, positive, and then positive. So those sign only. So positive 50i, positive 150, positive 150, and then positive 100. However, if we will choose the other symbol, so if it's the endpoint, okay, negative, 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 then you just have to change this one. So negative 50 I sub 1, negative 150, and then negative 100, which is also the same.
Ay,
Okay,
sir.
this another.
Kala ko pina-follow kasi natin yung arrow, hindi pala.
No, we don't follow that one. So again, if we have the same symbol for the this one, plus and minus for the I sub 1, and then plus and minus for the I sub 2, then it should be plus. Okay, so this sign will only have a negative, like for example, maybe, okay, let's say your R3 right here. So for the I1, he has this symbol, positive minus, and then for the I sub 2, right here, we have minus and then positive. Okay, so that's the time that we'll be having a different sign for the I sub 2. So positive I sub 1 and then minus I sub 2. All right?
Sir, okay, sir.
So are
Yung
we...
sa ano pa, yung sa 150, sir. Bakit I1 plus I2 yun, sir? Hindi ba dapat plus I3?
Yeah. So thank you for that one. I1 plus I3. Okay, right here. So I1 and then I3 on the other side. Okay, so are we clear with our equation number 1?
Yes, sir. Yes.
All right, so let's try to compare. So we have here plus 50 I sub 1, and then, so everything is plus. Okay, so let's check. So this is the first equation, 50 I sub 1 plus 100 I1 plus I2 plus 150 I1 plus I3. All right, so this is your equation number 1. And then if you're going to simplify this one, of course, just distribute this 100 to the I sub 1 and then 100 to the I sub 2. You will have this one, 100 I sub 1, 100 I sub 2. So the same with 150. You will have 150 I sub 1 and then 150 I sub 2. And then you can combine same terms, I1 and then I1, I2 and I1 and I1 only. Okay, so in fact, we have 3 I sub 1. So right here, we'll have 300 I sub 1, and then plus 100 I sub 2, and then plus 150 I sub 3. So this is now your simplified form of equation in loop number 1. All right, so are we clear so far?
Yes, sir.
All right, so moving on
Yes, sir.
with your, yes, okay, so moving on with your equation number 2, I guess, yeah, this is equation number 2. 50, wait, not yet. Okay, so in this equation, so this is a continuation of your loop number 1. You represent the common directions of currents by their sums through common resistors. So it's quite long. So I'll leave the reading part to you guys. So those are just basically the explanations on how did we end up with this simplified form of equation. Okay. And then we have here the loop number 2. I guess 100, 300, and then 100. 100. Yeah, so this is the loop number 2. Okay, so from here, I'll just copy this one more time. Okay, so now let's now proceed with our loop number 2. So KVL at loop number 2. Right? So in here, what did you choose? I guess it's positive. Yeah. So we'll just go with positive also for us to have the same answer. So right here we have, so let's start with 250 for now. So we have positive 250, okay, times I2. And then plus 100 times I sub 2. And as you guys can try here, they have the same sign. So plus I sub 1. Okay, so you have to consider the flowing, the current that is flowing on this component. So we have I1 and I2, which affects R sub 3, which is 100. And then for the last one, we have here positive 300. And then we have here I sub 2 minus I sub 3. Okay, so we now have here a minus sign. That is because they now have different symbols. Okay, equal to 0. So were you guys able to follow so far? And how did we get this equation coming from this loop number 2?
Yes, sir.
Yes, sir.
All right, so let's see if if we have the same equation. So yeah, 100 I1 plus I2, I1 plus I2, and then I2 minus I3. I2 minus I3. All right. So we have here the original equation of the number 2 or loop number 2. And then just distribute, and then you will have this one. And then combining the similar terms, then you will have 100 I sub 1 plus 650 I sub 2, and then minus 300 I sub 3. Okay. So yeah. So are we clear with equation number 2?
Yes, sir.
Okay. So I'm rushing now since we don't have enough time anymore. So we now only have 7 minutes. Okay, so for the last one, so using KVL, note how the second term in the equation's original form has resistor R force value of 300 ohms multiplied by the difference between I2 and I3. So that is why we have here I2 minus I3. That's because they don't have the same symbol. Okay, that's the one that is trying to explain right here. So we have opposing directions. And then what else? Spectre is nice. Right, so I guess that's not that important. So using KVL, well, that takes care of two equation. Okay, so this is now the third equation. Okay, so from here, he chose to have a positive. Okay, so let's have our third equation. Happy. Okay, so KVL at node KVL at loop 3. Okay, so we have here positive 24 volts and then negative 150 I sub 3. Okay, so again, we should add up those two currents since they are flowing with the same direction. So I3 plus I1. Okay, and then for the next one, we have here negative 300 times I sub 3 minus I sub 2. Since the I sub 2 is opposing the current of I sub 2, right? Equal to 0. So let's see if we have the same answer. So were you guys able to follow on how did we get this one? Are we clear? Double check if this one is correct or no. Hello guys. Do we have the same result with this one upon your, just by thinking it on your mind? Hello? Are we clear on how did we get this equation?
Yes, sir.
All right, so let's compare. Positive 24 minus 150 minus 300. 24 minus 150 minus 300. And then right here we have plus I3 and I1, plus I3 and I1, and then I3 minus I2. Okay, so there you go. So we've got the third equation. So just distribute the terms within parentheses and then combine similar terms, and then you will have this simplified form of equation. Okay, and then from there you can now perform the three equation three simultaneous equation. Okay, so just eliminate two variables or one variables and then come up with another equation, and then you'll be able to get the I sub 1, I sub 2, and I sub 3. Okay, so I wasn't able to show the result of this one anymore in here, so I'll leave the computation part on the I sub 1, I sub 2, and I sub 3 to you. All right. And then here's the reference where this one came from. Okay, so most of the information came from the allaboutcircuit.com. So make sure to visit this one. But I guess I have already I take everything from there. So that is why you will not see any difference. Okay, just the layout. Anyway, so this is the mesh current analysis summary. So as well as using mesh current analysis, we can also use node analysis to calculate the voltages around the loops. So again, reducing the amount of mathematics required using just Kirchhoff's laws. Okay, so there is another reference wherein you can also check, which also discuss a mesh current analysis. This one is electronic tutorials. So make sure to check this one also. All right, so that's it for the mesh analysis. So next meeting, we will compare our answers. Okay, so this will your assignment at the same time. Okay, so I would like you guys to answer the three equations, three unknowns, and then what are those three unknowns. All right, and I have also prepared, so I added three additional link in here wherein you can have or take a quiz or practice exercise. Okay, so make sure to visit those three uh, links, okay, or three website. So that will help you to understand more what is mesh analysis. Okay, and then so I'll just announce I'm not yet done with your Maxwell's quiz or mesh analysis quiz. So I will just announce, okay, whether this one is already published or not. Okay, so yeah, that's it for now. We'll just discuss the module 5 next meeting together with the answer of this example. All right, so any questions so far?
No, sir.
None, sir.
How about the others? Question,
None,
guys?
sir.
Okay.
Answer.
So again, just study, study, study. Search more examples, okay, especially the videos, okay, that I am including in here. So I have also added 3 YouTube videos in here. So make sure to check those links, okay. So mesh current problems, mesh current step 1 to 3. And for 7 and 8, so that's for superposition. So we'll just discuss that one next meeting. All right. Okay, so thank you guys for coming. So if ever you guys have a question or clarification, so feel free to message me anytime. Okay, so I'll just be able to read that one once I'll check my inbox. Okay, so goodbye and see you guys next week. Goodbye.
Bye, sir.
Thank you,
Bye,
sir.
sir.
Thank you,
Bye.
Thank you,
sir.
sir.
Thank you.
Bye, sir.
Goodbye.
Sir,
Yes.
pwedeng extend yung quiz?